Welcome. In this explainer, we're setting off on a quest. Really, a quest to pull back the curtain on one of the most powerful ideas of our time, statistical learning. We're going to figure out how we get to that perfect prediction. You know, you hear about algorithms learning all the time, right? From what movie you should watch next to which stocks to buy. But it all really boils down to this one central question. How does an algorithm actually learn from data? What's really going on under the hood? At its very heart, all of this is about a search. It's about looking at a giant mountain of data and trying to find that hidden pattern, the secret relationship that connects everything together. So, what are we really talking about here? Well, statistical learning is basically this huge toolbox, and the whole point of these tools is to understand data. At its core, it's all about finding the relationship between some inputs, we'll just call them X, and an output we want to predict, which we'll call Y. And believe me, this simple idea is the engine behind pretty much everything, from your streaming recommendations to super complex financial forecasts. Okay, let's picture this. Think of it like a machine. On one side, we feed in our inputs, our X's. This could be anything, like the size of a house or yesterday's stock price. They go into this magic function, F, which for now is kind of a black box. Then, out the other side pops the output, our Y, the house price or tomorrow's stock trend. Of course, there's always a little bit of random static or noise we just can't predict. The entire quest of statistical learning is just to find the best possible guess for what that magic function F actually is. So before we even try to build that function, we have to make a choice, a really crucial one. This is like the first big fork in the road on our quest. Are we just trying to predict what's going to happen? Or are we trying to understand why it's happening? And this slide just lays out those two paths perfectly. Over on the left, we've got prediction. Here, that function F can be a total black box. We don't really care how it works, as long as it spits out the right answer. We're just asking, will this customer leave? Simple. But then, on the right, you have inference. Now, we absolutely have to open that black box, because we need to understand the why. The question completely changes. It becomes, which factors are actually causing customers to leave? Okay, so we've picked our goal. The next step on our quest is to look at the kind of map we've been given to work with. Because, you see, the type of data we have totally changes the type of learning we can do. And there are two main flavors. First is supervised learning. This is where our data comes all nicely labeled. For every input, X, we already know the correct output, Y. It's like being handed a map where every city is already named. Our job is just to learn the roads that connect them. Then you've got unsupervised learning. This is where the data is just, it's unlabeled. We've only got the inputs, X. This is like getting a map with just a bunch of dots on it. No names, no borders. The goal here is to find the hidden structure all on its own, maybe grouping those dots into what look like countries or regions. Let's make this a little more real with some examples. Predicting if the stock market will go up or down based on past data? Yep, that's supervised, because we have all the historical answers. Trying to estimate someone's salary based on their age and education? Also supervised. But what about grouping patients based on their genetic data without having any idea what diseases they have beforehand? That's unsupervised. We're asking the algorithm to find the hidden patterns for us. All right, now we come to what is probably the single biggest danger on our quest. It's this tricky trap where trying to make a perfect map of the past can actually lead you completely off a cliff when you try to navigate the future. It's called overfitting. And this is the absolute heart of the problem. A model that has perfectly memorized every single twist and turn of the data it's already seen is often terrible at predicting what's going to happen with brand new data. Why? Because it hasn't just learned the true pattern, it's also memorized all the random, meaningless noise that was in that specific data set. In a high-stakes field like medicine, an overfit model could be a disaster. It might misdiagnose a patient because it focused on some random quirk in their test results instead of the real signal of the disease. This slide visualizes the problem perfectly. As our model gets more and more complex, more flexible, its error on the training data it already knows just keeps going down and down and down. That's the line sloping down. But, and this is the big but, look at that U-shaped curve. That's the model's error on new, real-world data. If the model is too simple, the error is high. If it gets too complex, the error is also high again. That's overfitting. The sweet spot, our actual goal, is right there at the very bottom of that U. So this brings us to the climax of our journey, the fundamental trade-off that every single person working in data science faces every single day. It's the ultimate balancing act between two powerful competing forces. And these forces are called bias and variance. Think of it like archery. A model with high bias is way too simple. It's like having a faulty bow that always shoots to the left of the target. It's consistently wrong in the same way. A model with high variance is the opposite problem. It's too complex. It's like an archer with a really shaky hand. The arrows land all over the place. It's unpredictably wrong because it's reacting to every tiny twitch and breeze, all the random noise in the data. This means the total error of any model is really made up of these three things: bias squared, variance, and something we call irreducible error. Now that last part is just that random noise we talked about, the static in the world that no model, no matter how good, can ever predict. Since we can't get rid of it, our entire job is to find the perfect balance between bias and variance to make their combined error as small as possible. So, to wrap up our quest, here's your summary. First, you've got to define your goal. Are you predicting or are you trying to understand? Second, know your data. Is it labeled or not? Third, and this is the big one, you have to find that sweet spot, balancing the trade-off between a simple model and a complex one. And finally, and I cannot stress this enough, you have to always test your model on data it has never, ever seen before. That's the only true measure of whether you've succeeded. Which leaves us with one final, really fascinating question to think about. As we get more and more data, the temptation is always to build more and more complex models. But the core challenge never really changes. How do we choose the right balance between a simple story that might miss a few key details and a really complex one that might just be explaining random noise? Finding that balance, well, that's the real art and science of statistical learning.